Good evening again. It barely seems like 5 minutes. I was last here talking to you all, so here we go again. This is another short talk on exploring the solar system, but this is about exploring other solar systems, exoplanets, meaning planets around other stars, not our own. So why should we bother looking for exoplanets? How do we go about finding them? We know that stars are out there, but how do we know that those stars have planets? How do we go about looking for life? And what are we doing about it in terms of what missions are coming up in the near future? So, as you can see from the solar system there, the orrery sitting on the front table, we can ask ourselves, well, we know what planets we've got in our solar system, but we can ask ourselves all sorts of questions like, where did all the planets and the asteroids and the moons, where did they all come from? And is our solar system typical? If other stars have solar systems, do those solar systems look anything like the solar system that we know and love here? Are there other planets like the Earth? If there are other solar systems out there, do any of those solar systems have planets that look like Jupiter or look like Saturn, or perhaps more importantly, other planets that look like the Earth? And if there are other Earth-like planets out there in our galaxy, is it possible that some of them do harbour life? And we hope that studying other solar systems elsewhere in the galaxy will help us understand our own solar system. So how do we go about finding them? Well, there are various methods. It might get a little bit technical, so I'm going to skip through these fairly fast and happy to take questions afterwards. There are various ways we can look for planets around other systems. Because all of the planets are orbiting, if they exist, a planet orbiting another star, the star will get tugged and move slightly backwards and forwards, especially if they've got a big planet like Jupiter. As Jupiter goes round the star will wobble slightly as the planet goes round. It's called radial velocity, but effectively what we're looking for is the wobble of a star. It might only be a small wobble, but in principle we can see it. The second one is transits, in which if we're looking at a solar system, let's imagine that we happen to be looking at this solar system edge on, every once in a while a planet might move in front of the star, and hence the light from the star will be dimmed because of the transit of a planet in front of the star. So we're effectively looking for shadows. If we look at the brightness of a star, if we see it dip, that might be an indication that a planet has moved in front of the star. And relatively recently, it's been possible to do direct imaging. The main problem with actually seeing a planet around a star is not necessarily the distance, it's the fact that planets are much fainter than stars. The stars will produce an awful lot of light, and a small amount of that light gets reflected off the planets if they exist around a star. And because the planets are relatively close to a star, and the star is so bright, perhaps 1,000,000 times brighter than the planet, we'll never see the planet because of the glare of the star. It's like looking some distance away at a searchlight and trying to see a tiny firefly that's buzzing around the searchlight. If the searchlight is really bright, it's very difficult to see anything much fainter close by. But there are ways we can deal with that. And the other two techniques, they're in the handout if you want to learn about them, but I'm not going to say anything about them this evening. So how do we look for wobbles? If we've got a planet going around a star, because if the planet is massive enough, it makes the star wobble. If we look at the light from the star, we may not be able to see the planet, but if the star is moving towards us or away from us because of the wobble produced by the planet, we can see a change to the light produced by that star. The indication at the bottom here is that the star turns blue or the star turns red. It's not quite as simple as that. A slightly better way of thinking of it is to think of the spectrum. If we take the light from the star and spread it out into a rainbow, then as the star is moving towards us or away from us, we see small changes in the spectrum towards the red end of the spectrum or towards the blue end of the spectrum. It's called the Doppler shift, and it's a known physical phenomena. We see it in the laboratory, so we understand it. And if we see this so-called Doppler shift, this movement towards the red or towards the blue, then we can figure out the stars moving towards us or away from us, and hence we can figure out what planet must be going around that star in order to make it wobble in this particular way. Transits are a little different in that we're not looking to see what the star is doing, other than we're looking at the light output of the star. And the light output of the star drops if an opaque object like a planet, moves in front of the star. So the star's brightness goes down and then a little while later comes back up again. Maybe a few minutes, maybe a few hours later, depending on which planet is going around the star. And if we have a very big planet going around the star, it blocks more of the light because it's just a bigger planet. It's a bigger object moving in front of the star. And so the depth of how much does the brightness go down will be greater than in the case of a small planet going around the star. So by looking at how much the light drops, and it doesn't drop by a huge amount, it drops by maybe 1%. Or 0.5%. It's a tiny drop, but as long as we measure the starlight accurately, we can see the drop and we can deduce, or at least we can guess, we have an estimate of how big the planet must have been in order to produce that much drop in the light. So the wobble depends on how massive the planet is, but the transit, the shadow produced by an object moving in front of the star, that depends literally on how big it is. Not the mass of the planet, but just what its diameter is. It works, it's a little more complicated, but it works even if we have lots of planets going around the star. So here, for instance, we have 3 planets, and so the light drops, and then as this planet moves away, it comes back up again, and then we have a couple more planets that are coming round, and so the light drops, and then drops again because of a second planet. So it gets a little more complicated. But if we look at starlight and we measure it accurately and we look at it for long enough and we look at these various drops, then we can deduce what planets exist and how many planets exist. So it's not just good for looking at one planet around one star, we can actually get information about an entire solar system around stars. This gives you an idea of what it actually looks like in practice. Again, if we think about an object moving in front of the star, the light dips, and these blue dots are an indication of what we actually measure, and hence we deduce that the light has changed according to that white curve there, based on the blue dots, which are actual measurements of the brightness from a star. If we look at actual data, this is what this is the James Webb Space Telescope looking at the light from a star, virtually constant, and then it dips, and then it comes back up again. And so the James Webb Space Telescope has been looking at the light from various stars, looking for these dips, and from that we can deduce the existence of various planets around various stars. The third technique, the direct imaging one, is a bit tricky, and it relies on the fact that if we're looking to see what's going on, let me just, go that again, the star is so bright we can't see what's going on unless we block it out. If we block out the light from the star, then we realize there's actually a very faint planet sitting next to it. That's rather tricky because it means that we have to, inside our telescope, very precisely put a small blocking circle, a little so-called occulting disk. We put that disk in just the right place to block a star and then see if we're left with anything just outside that disk. So it can be fiendishly difficult, but here a disk has blocked out the light from the star, and what we're left with is apparently 4 points of light. Let me just run that video again. 4 points of light, the closest one moving quite fast, the more distant ones moving more slowly, just as we see in our solar system. So the very bright starlight has been blocked out so as to reveal the fainter planets going around that star. It works if they are edge on as well. So here we've blocked a star and there's a planet going around the star, which we can't see when it's in front or behind, but we can see when it's, as it were, peeking out one side or the other. We block the star and then we look for the planets going round the star on one side or the other. And this you probably didn't notice, but this is a time lapse taken over many months or years because, of course, the Earth goes around the Sun in 1 year. Other planets might go round their star in less than a year or more than a year. So we have to do these experiments over an extended period of time to identify other solar systems. The James Webb Space Telescope, again, by blocking the light from the central star, has revealed here a solar system not with individual planets visible as tiny dots. It appears to be this solar system is a huge ring of dust. Perhaps this is a solar system still in the process of formation. We think our solar system started as a huge dust ring, which eventually condensed into the planets we see today. So maybe we're looking at the early stages of a solar system, not one with planets, probably not one with life, but studying these sorts of systems tells us about how solar systems come into existence. This one appears to be not just a uniform dust ring, it appears to have different rings inside it, different structures. Perhaps what we're looking at here is very similar to what we would call an asteroid belt or the Kuiper belt. The Kuiper belt, the region beyond our dwarf planet Pluto. So maybe there are structures in there, but as far as we can tell, there are no individual planets in that dust ring. So what can we tell about exoplanets? In principle, if we can look at the wobble, we look at the spectrum of light, we break it down into the colours, we can tell the wobble of the star, which tells us about the mass of the planets that are going around the star. And if we look at transits, as the planets move in front of the star, we can get information about the size, the diameter. If we're lucky, we can do both on the same system. It's really useful if we can see the wobble and see a transit. Because the techniques tell us different information, the wobble tells us about mass, transits tell us about size. Also, if we break the light down from a distant planet and star using a prism or using a diffraction grating to spread the light into a spectrum, we can also get information about the atmosphere as well. But what's really important is if we have the mass and if we have the size, then we have an estimate of the density, because we can have perhaps big planets that aren't very massive, i.e. low density, and vice versa. If the density is very high, maybe this planet is a rocky planet like the Earth. If the density is very low, maybe it's a gas. If the density is somewhere in the middle, maybe it's a liquid, an ocean planet. So having the mass and the size is very useful to give us an idea of the composition, the type of planet that we're dealing with. And if we can work out how far the planet is from its host star, then given that we can measure the temperature of the star just by looking again at its spectrum, we can tell whether it's a really hot blue star or whether it's a relatively cool red star. If we can work out how far away the planet is, we can get an idea of what the temperature of that planet is. If it's very close to its host star, it's probably quite warm. If it's a long way from its host star, it's probably quite cold. And so temperature will tell us whether we're dealing with perhaps an ice planet or perhaps a lava planet, depending on whether we're talking about really low temperatures or really high temperatures. And so far, we have found lots of exoplanets. We haven't studied every star in the sky to see if they've got exoplanets. But of the ones that we have studied, it looks like planetary systems are much more common than we first thought. When I was a lad, it wasn't clear whether or not we could expect every star to have a solar system, to have a planetary system. Now it looks like they are very, very common. And it's even possible that there are a huge number of Earths out there as well. The exoplanet zoo is absolutely huge. That is not it. That is just a small selection of all the exoplanets that we've found. It's been estimated that there are something like 5,000 that are currently documented, meaning that we have the mass and the size and an indication of the temperature. That doesn't mean there's only 5,000 out there. It means of the small number of stars that we've studied, there are many, many thousands of exoplanets. Maybe 1,000 of them are in this particular graphic. They are arranged, roughly speaking, to scale, so you can get an idea of the large ones and the small ones, and they are arranged in temperature as to cold on the left and hot on the right, based on how far away they are from their host star. So the ones on the right are probably quite close to their star, the ones on the left are probably a long, long way away. If we're, just to give you an idea of scale, there's a few planets down the bottom left which aren't technically exoplanets. For instance, we've got Saturn, Jupiter, Uranus, Neptune, etc. They're there just to give you an idea of scale. And Earth, Mars and Venus are in there as well. But if we're interested in those which might harbour life, then we want to restrict ourselves to what temperature range do we think will give rise to liquid water. Anything way over on the left is too far away from the host star to keep water liquid. Doesn't stop you having moons with liquid water, but the planet itself wouldn't have liquid water. Those on the right would be too hot. The water would boil and it would go to vapor and simply evaporate. So if we're interested in planets that might harbor life in the way we understand because they have liquid oceans, then we ought to be looking in that particular strip there. So for instance, just to give us an idea of scale, Mars is too far away from the sun, it's too cold. Venus is too close to the sun, it's too hot. And not surprisingly, Earth is actually sitting there. So again, that gives us an idea of what we should be looking for. But if we go back to all of these exoplanets and have a look at what sort of interesting exoplanets do we find out there, one thing I found quite surprising was that when we looked at our nearest star, other than the Sun, Proxima Centauri has a planetary system. This is only 4 light years from Earth. That's as close as it gets. Most stars are hundreds or thousands or tens of thousands of light years from Earth. This is the closest one, and yet our immediate neighbour has a planetary system. That tells us that it's not that uncommon, unless we were just really lucky to find that our immediate neighbour also has a planetary system. This is one of the oldest ones that have been found. It's given the rather interesting name of Methuselah simply because nobody wants to keep calling it PSR B162026b. But it's one of the oldest planets ever found. We estimate this planet as being 12.7 billion years old. The Earth is about 4.5 billion years old. So this is almost 3 times the age of the Earth. It implies that planets came into existence very, very early on in the universe, because the universe is only 13.8 billion years old. So some planets, it would appear, came into existence really, really quickly after the universe began. So planets aren't something that only have come along in the last few billion years. They've been sprinkled throughout all of our understanding of the universe's history. In the top right, the right-hand edge here, that's where we've got very hot planets. The top right, the surface temperature is a ridiculous 4,000 Kelvin. If you think it was hot a few weeks back, no, this is much, much, much hotter than that. We're not even talking about liquid water being vaporized. Most metals would be vaporized at this sort of temperature. So there's no real thought of life existing on a planet this close to its host star. The one in the bottom right looks a little bit egg-shaped and distorted. That's real because this is so close to its host star, it's being stretched out into a sort of egg shape because it's only a few million kilometers from its star. We here on Earth are 150 million kilometers from the Sun, so this is much, much, much closer to its host star, getting stretched out. What other interesting objects do we have in the exoplanet zoo? Well, in the top right there, we have the wonderfully named HAT-P67b. They've really got to get some better names than these. This is a really big one, as you can see. It's basically the largest one in this particular collection here. It's much bigger than the planet Jupiter, just for comparison, but it's much less massive than our planet Jupiter. So if it's much bigger, but less massive, that means it must be very low density. It's not sort of density of Earth, which is much higher than the density of water. It's thought that this object would be about the same density as marshmallow or something like that, a very low density material. So we're not quite sure how a planet like that comes into existence. And finally, they got themselves sorted out when they got to naming these planets, because after deciding that HATP67b is a ridiculous name, it sounds like some scientists got together and said, let's get some better names for these exoplanets. And then they come up with Coconuts 2b. That's probably my favorite. If you're going to name a planet, call it Coconuts. It actually stands for Cool Companions on Ultra-Wide Orbits. I think they've been engineering that backwards from let's get an acronym and then see what we can make it fit. So here, this is a planet that's so far from its from its host star, 7,500 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun. So this planet is further from its star by a factor of 7,500 compared to the distance from Earth to the Sun. And instead of going round its star in 1 year like we do, it goes round its star in 1 million years. So the idea of seasons, for instance, would be geological time rather than our seasons, which keep repeating every 12 months. And perhaps my favorite is LHS 1140b, that one in the middle there. This is thought to be an ice planet, but it's relatively close to its star. It can still be ice because the star isn't particularly bright, doesn't produce a lot of heat. So it's ice even though it's relatively close to its star, but it's thought to be tidally locked. Like our moon always faces one face towards the Earth, so this planet always has one face towards the star. So it's ice, but it's thought that if one face is always pointing at the star, it's possible that the middle of the ice that's pointing towards the star, maybe that will melt. So it might end up looking like that. An ice world, but with a little bit of an ocean in the bit of the world that happens to be pointing directly towards the star. And you can see why it's ended up calling the eyeball planet. This is a little bit of an artist's impression, but it's based on scientific evidence that we think it's made of ice. We think it might have water because of its distance to its host star. So there's an awful lot going on. There's an awful lot of missions that are out there that are looking for planets. Some of them find them by accident. So for instance, Gaia is a spacecraft that's designed to map the positions of stars in the Milky Way. But along the way, because it's doing it over a period of time, it might notice that some stars appear to be wobbling. And if they're wobbling, they're probably wobbling because planets are going round them. So the Gaia spacecraft has actually found some exoplanets, as it were, by accident. And the James Webb Space Telescope is an infrared telescope that was launched a few years ago now, back in 2021. And that has been told to go and look at these objects because they look quite interesting and we think they might have planets going around them, and then it can do some direct imaging. But in addition to those 2 missions, there are also other missions that are explicitly missions to find exoplanets. Some of them have been around for a while. Kepler has found thousands of exoplanets around a lot of stars, and there are a number coming online soon. Notice that we've got a European Space Agency mission coming online fairly soon, 2026. That's when it's due to be launched. I believe that's still on schedule. And there is a Roman telescope, Nancy Grace Roman, a NASA telescope due to be launched in 2027, which maybe Trump is going to be cancelling, we're not too sure, but hopefully that will still fly. If the politicians can sort themselves out and make sure that NASA is fully funded, then the Nancy Grace Roman telescope will fly in 2027. That's quite an interesting one because they had this idea that if we're going to look directly for planets, rather than try and block the starlight when it's in the telescope to block this bright starlight so that we can see any exoplanets going around, what if we actually don't do it that way? What if we block the starlight so that we can see exoplanets by having a disk not inside the telescope, but what about if we had a star shade outside the telescope? What if we launch the telescope and with it launch a star shade which would then unfurl in space and it would end up 100 meters in diameter? And then we fly it a long way from the telescope. We fly it 50,000 kilometers away from the telescope and very carefully position it so that it blocks the light from a distant star. And when it blocks the light from a distant star, we would then be able to see any exoplanets that are going around that star. So a rather ambitious idea, the idea of using a star shade outside the telescope. It stops the light from the star entering the telescope. If the light enters the telescope, it gets scattered and it makes it very difficult to see the exoplanets. But you then have the problem of getting a star shade to unfurl in outer space and then positioning it in exactly the right place so that you block a star as seen by the telescope. So hopefully in a couple of years, the Roman telescope will be launched. The star shade won't necessarily be launched at the same time, but it's a very interesting idea. I said I'd finish by talking about looking for life. How do we go about looking for life? Well, planets can transit in front of a star or get eclipsed behind a star. And if we look at the light coming from the combined star and planet, when the planet disappears behind the star, we no longer get the light from the planet. So if we look at the spectrum of light we're receiving before and after an eclipse, we can get an idea of what light is coming from the planet. And if the planet has an atmosphere, then the starlight, when the planet transits, will come through the atmosphere and some particular wavelengths might be absorbed. Wavelengths absorbed because of some molecules that exist in the atmosphere of a planet. And if we look at James Webb Space Telescope data, if they look at the dip from a transit but look at different wavelengths, here it's blown up at the bottom, the depth of the transit will depend on the wavelength. Some wavelengths of light, some colors of infrared light if you like, are absorbed preferentially by the molecules in the atmosphere of a planet. So we can tell even a planet that's thousands of light years away, we can tell if that planet has got an atmosphere which contains carbon dioxide or water or methane or other molecules. And that's what the James Webb Space Telescope has done. It's effectively started to identify the chemistry of what's going on in atmospheres of other planets around other stars. The fact that it's possible to do that is absolutely amazing. Of course, we still need to interpret this. We still need to look for unequivocal signs of life generating certain molecules. If we look at the Earth's atmosphere, we find oxygen and methane and carbon dioxide in a particular mix. If we find that same mix in an Earth-like planet, that could be an indication of life on that planet. So that's what various missions and various telescopes are looking for to see if there's life out there. Just to give you an idea how things have changed in the last few years, when I was a nipper, we didn't know whether planets existed or not around other stars. Here we're plotting as a dot any planet that exists as a function of how massive it is. Big ones at the top, massive ones at the top, less massive ones at the bottom. And on the horizontal scale, how far are they from their host star? So here we've shown our own solar system, Earth and Venus, Uranus and Neptune, Saturn and Jupiter. Let's run from 1992 up to the present day and see what planets have been found. To start with, not many in the 1990s. But as we go into the current millennium, in the noughties, we start seeing lots of planets. And as Kepler comes online, Kepler, a spacecraft designed to find exoplanets, there is suddenly a huge number of these purple dots indicating these have been found by the Kepler spacecraft. So now that we are here in sort of 2024, I think is the last date this graphic goes up to, you can see that there are thousands and thousands. Each dot represents one planet that we know about, and we know about its mass, and we know how far it is from its host star. They appear to be clumped, as if maybe some planets are more likely than other planets. But we have to be careful, because some planets are easier to see than other planets. It's relatively easy to see a Jupiter-like planet in another star system. It's rather difficult to find an Earth-like planet in another star system. So just because we've got lots of them and they appear to be clumped into various masses, that doesn't mean that's what's actually out there. It means those are the ones that are easiest to see, and we have to bear that in mind. So again, if you want to know more information about every planet around every star that we know about is documented in a NASA dashboard. They basically say this planet has got this mass, this size, is going around the star at this distance, etc. Every planet's information is available if you want to go and browse. I've also said there's very interesting explanations in the Exoplanet Archive, and very soon we're going to have a European Space Agency mission called Plato. Very soon, we hope, we're going to have a NASA mission in 2027, and way down the line in years to come, we're going to have more exoplanet missions. So if you want to know more about why and how we go about observing planets around other stars, go and look at these web addresses. Again, the handout gives you the web addresses for you to go and have a look and find more information. Thank you very much for listening.